Hi, I am Mukunda Bharatheesha from Delft University of Technology. I am excited to talk to you about our contribution RRT-CoLearn, a new algorithm for sampling-based kinodynamic planning. Sampling-based planners, such as the rapidly exploring random trees, face two important challenges that significantly impact their overall planning times. The first challenge is the computation of the distance metric in the nearest neighbor step of the RRT, and the second challenge is the computation of the steering input in the extend step of the RRT. Both problems require solving one or more optimal control problems that are computationally expensive. As a result, the planning times of standard kinodynamic RRTs is very large and renders them practically unusable. In recent years, however, a new class of algorithms called learning-based RRTs have been proposed that provide promising avenues to address these challenges. The basic idea of a learning-based RRT hinges on an offline data generation and learning phase and an online planning phase. In the offline data generation and learning phase, a database of several locally optimal trajectories between random state pairs and their corresponding costs is generated. This data is subsequently used to learn a generalizable mapping between state pairs and the cost. The result is a speedup of up to 3 orders of magnitude in the nearest neighbor step of the RRT and also realistic planning times. However, from the perspective of practical usability, there are still a couple of key aspects with the preliminary idea of a learning-based RRT that influence the overall planning times. The first aspect is there is still one more optimal control problem to be solved at each extend step of the RRT, as only the distance metric is learned previously. The second aspect is the data generation time. Although offline, it is quite large due to the use of numerical trajectory optimization or direct optimal control. Our algorithm RRT-CoLearn precisely focuses on these two aspects by leveraging the indirect optimal control approach for the data generation step. This key idea provides a powerful twofold advantage. The first is an analytical formulation for the generation of locally optimal trajectories via a simple numerical integration, and second, a learnable representation of both the distance metric and the steering input. As a result, we achieve a further speedup of an order of magnitude in the overall planning time compared to the current state of the art. At the same time, the offline data generation phase is also sped up significantly as there is no need for numerical trajectory optimization. If you are interested to know further, I invite you to our poster. I will also be glad to hear from you on my email or on our project's source repository. Thank you.